Hey guys, and welcome to my A-level physics revision video, continuing with section 1 in this video looking at particles and antiparticles and particle interactions. So let's begin with particles and antiparticles. Every particle, such as the proton, the neutron, the electron, and all the other particles, all have a corresponding antiparticle. And say for these three examples, the antiparticle of the proton is simply known as the antiproton. Antiparticle of the neutron is known as the antineutron, and the antiparticle of the electron is actually known as the positron, which we write with a little E plus right here. Technically there should be a little minus there to show that the electron is negatively charged and the positron is positively charged. So the only difference between particles and antiparticles is that they have opposite charge to that of their corresponding particle. Everything else about them is the same. They have the same mass and they have the same other particle properties, which we'll have a look at more in future videos. Now, when particles and antiparticles collide, they will annihilate and emit radiation. So say we have an electron and a positron, and say they're heading towards each other, and when they hit each other and collide, they will annihilate and release energy that's in the form of electromagnetic radiation. And this electromagnetic radiation is normally in the gamma range part of the spectrum. You can actually produce these positrons by what's known as beta plus decay. And in the last video I mentioned beta minus decay, in which you have a neutron turns into a proton plus an electron plus an electron antineutrino. So that's basically the standard equation for beta minus decay. Now beta plus decay, actually almost the opposite happens. You have a proton changing into a neutron, but instead of releasing an electron, you actually get a positron. And instead of an anti-electron neutrino, you actually get just a normal electron neutrino. Now, antimatter was first predicted in 1928 by the English physicist Paul Dirac in his famous equation known as the Dirac equation. Now, Dirac equation is quite a long and complicated equation, so thankfully you don't need to know it for A-level. But antimatter then went on to be discovered a little while afterwards, after it had been predicted. However, before then, it was Einstein that showed that energy and mass were linked by his famous equation, E equals mc squared, which said that there was a large amount of energy locked away in a small mass. And it's that energy that gets released in the form of a gamma ray photon when a particle and an antiparticle collide. So let's draw a diagram of this. So you have an electron and a positron that are colliding. So they're moving towards each other. And when they move towards each other, they actually produce two gamma ray photons. And the energy of these two gamma ray photons combined is equal to the energy that corresponds to these two electrons, which is locked up in the form of their mass. So electrons, of course, are really, really light particles. Because there's so much energy per unit mass, because of course they're linked by this constant here, which is the speed of light squared. Speed of light was a massive number, of course, but the speed of light squared is going to be, what, 9 times 10 to the 16, just 3 times 10 to the 8 squared. You're going to get a humongous amount of energy being released from these two particles. And so That's why it's in the gamma range of the spectrum. But we can also consider this the other way around, in which rather than mass gets converted into energy, we can have energy in the form of electromagnetic radiation being converted into mass. And this we refer to as pair production. So say we have a high energy gamma ray. Now that will actually turn into two particles, one of which is an electron and one of which is a positron. And you always get it like this. You can't create matter without antimatter. It always happens in pairs. Now, a lot of the time in physics, you may see that some of the energies that we're talking about here are not given in the standard SI unit of joules, but rather in this funny unit called electron volts. So what's an electron volt? Well, an electron volt is defined. It is defined as the energy needed to accelerate an electron through a potential difference of 1 volt. And 1 electron volt is exactly the same as saying 1.6 times 10 to the minus 19 joules. Now you might recognize this number right here, 1.6 times 10 to the minus 19, and this is the charge on an electron. Now later on in the course, there is an equation which states that energy equals charge times the voltage. And that's quite a big equation in A-level physics. And that's basically saying that charge is the energy per unit volt. So if you have 1.6 times 10 to the minus 19 coulombs multiplied by a potential difference of 1 volt, then you're going to get 1.6 times 10 to the minus 19 joules, which is the same as an electron volt. So now let's consider the energies involved in annihilation and pair production. In annihilation, we've got the two particles which, from Einstein's equation, have what's known as rest energies. We normally denote rest energy by the little term E0. Now, these two particles will then annihilate and produce two photons, which have energy hf min. And f min is the minimum frequency. We can equate these two energies saying that 2 E0 equals 2 hf min. And if we divide both sides by 2, we get that E0 equals hf min. Whereas E0 is simply E0 equals m, mass of the particle, in this case we're dealing with an electron, times the speed of light squared. That is the rest energy. It's the energy that's locked up within an electron due to its mass. And that corresponds to a frequency f min. And that minimum frequency is normally in the gamma ray part of the spectrum, which is why you need radiation with enough energy to get to this rest energy here. Now with pair production, we have a photon which is travelling with an energy of hf min. But this becomes two particles which must each have rest energies E0. But since there are two, the photon actually has to have enough energy to produce two, since you can't have a particle without an antiparticle. So therefore hf min in this case is equal to 2 E0. So with annihilation, the minimum frequency is just E0 divided by h, if we just divide both sides by h in this equation. Whereas with pair production, the minimum frequency is 2 times E0 over h. So you actually have to have a a higher energy, a higher frequency moving gamma photon or gamma ray to produce particles, since you have to have the two. Any photon with less energy would not have the sufficient amount of energy to produce a new particle pair. So now let's move on to particle interactions. how do particles interact at this level? Now, we know classically that an object, say we have a block here, this object experience many forces. You know, it might have the force due to gravity, it might have some friction, might be, I don't know, it might be hung from a ceiling, so there might be some tension in this wire. We'll cover all of this in the section on mechanics, and you'll learn then how to resolve forces. But this doesn't really apply at the quantum level. So how does it work? Well, let's say we have two electrons. So these are both electrons, E minus, E minus. Now we know that electrons are negatively charged, and therefore there's going to be some kind of force that's going to repel these two electrons from one another. But the question is, how do these electrons know that there's another one that's close by to cause them to repel? Well, it was the famous physicist Richard Feynman who worked out how this happens. And he said that between these two electrons, so these are the same two electrons, they actually exchange a photon between them. And that photon lets the other electron know that it's there, and therefore it knows to move away from the other. Now, we describe this photon as being virtual because we can't actually directly detect this photon. If we tried to, then we would actually prevent the force between the two electrons from acting. Now, we can represent these interactions by what's known as a Feynman diagram, and you'll need to know how to draw Feynman diagrams as part of this course. So let's draw a Feynman diagram for two different electrons, and as we do so, I'll talk you through the rules. So all incoming particles on a Feynman diagram all come in from the bottom. So in this case we have two electrons that are entering from the bottom. So we draw that. Now, what's coming out of this interaction? Well, just the same two electrons. There aren't actually any changes in particles. In a second we'll draw what happens when there is a change of particles, but in this case we just get two electrons coming out. So two electrons coming in, two electrons going out. But of course we need to represent this photon right here, and this we represent by a wiggly line, just like this. And for the photon, we normally use the symbol gamma. It's just a convention. It's not necessarily this. It doesn't necessarily mean that it's part of the gamma part of the spectrum, but we just normally use the symbol gamma to represent a photon. A little bit confusing, I know. So this is how, in principle, a Feynman diagram works. You've got the incoming particles coming in from the bottom, the outgoing particles coming out from the top, and you've got the interaction represented as a wavy line. Now this photon here represents the electromagnetic interaction between two electrons. But there is actually another force that's happening at this level, and we said before that there is the strong nuclear force that binds the nucleus of an atom together. But what actually causes, in beta minus decay, a neutron to transform into a proton? It can't be the electromagnetic force, since the neutron is uncharged, so there has to be another force at work. Now we call this force the weak nuclear force. And in beta minus decay and beta plus decay, a new particle and a new antiparticle are created, but they're not a corresponding particle-antiparticle pair, as one is an electron or a positron and the other is a neutrino or an antineutrino. Now, neutrinos hardly interact with other particles since they have no charge, but you very occasionally get them to combine with protons and neutrons. And we can draw this interaction between neutrinos and between protons and neutrons. So firstly let's draw what happens when we have There's our two incoming particles. We've got a neutron coming in. We're going to do the neutron-neutrino reaction. So we've got a neutron coming in, a neutrino coming in. This is an electron neutrino. There's actually 3 different types of neutrino, which is why I've been using the subscript nu sub e. This little Greek character here is known as nu. And so you've got the neutron coming in and the electron neutrino coming in, and they interact. And what do you get out of this reaction? Well, we get a proton coming out, and we get an electron going out as well. Now, we said that in the electromagnetic interaction, the exchange particle, the virtual exchange particle, was the photon. But what is it in the case of the weak nuclear force, which is responsible for this interaction? Well, it's called the W, in this case it's the W minus boson. Now let's do the other very similar interaction. This time we've got a proton going in, and rather than a normal electron neutrino, we have an anti-electron neutrino, and they interact a bit like this, and you have a neutron coming out, and on this side you have a positron coming out. Now notice that all protons and neutrons, which are actually collectively referred to as baryons, we'll come on to this a little bit more later, are all on the left hand side, and all of these guys right here are leptons, and they're all on the right hand side. And this is a convention used with the Feynman diagram, but we'll go over all those definitions in a lot more detail when we cover that. And instead of the W minus boson causing this reaction, we have the W plus boson. So what are these W minus plus bosons? They're the exchange particles responsible for the weak interaction. Now, unlike photons, which have no mass, these particles are very heavy, and so they have a much, much shorter range. So I'm now going to draw out 2 more interactions, and this time I'm going to draw out the beta minus and the beta plus reactions using this. Now that we know the force responsible, we can draw out the beta minus and the beta plus. So let's start with the beta minus interaction. This is probably one you'll have to know. So we have, in the beta minus, we have a neutron going in, and what's going out? We have a proton that's going out, and they interact via the W minus boson in this case. The easy way to remember it is a W minus boson corresponds to an electron going out, and if you have a W plus boson, you have a positron going out. So the sign of the W boson is the same as the sign of the electron that's leaving. So that's an easy way to remember it. So you have the electron going out like this, but of course we also have the anti-electron neutrino that's also going out. So you see all of these particles going out. So rather than having 2 in and 2 out, you have 1 in and 3 out. But because of course you have baryons on the left and leptons on the right, then protons on this side and the electron and the anti-electron neutrino are on this side. Now, technically, I'm not sure whether they're that fussed about it, but because this is an antiparticle, there is a convention that you should technically draw the arrow going that way rather than that way. Now, this is something, I don't know if they're too fussed about it, but technically that would be the right thing to do. So let's just finish this off. Let's do our Feynman diagram for the beta plus decay. So rather than a neutron turning into a proton, we have a proton that's turning into a neutron. So there's all our baryons on the left. Here's our little wiggly line, and we have the the W plus boson, which is the exchange particle responsible for this reaction. And we have our positron leaving, as well as our normal electron neutrino. And again, technically this arrow, because it's an antimatter particle, the positron, it should be technically going in. But again, I don't think they're too fussed about that at A level. Now, there is also a final type of interaction involving the weak interaction, and this is known as electron capture. So before I do the Feynman diagram for it, I'll just do a brief schematic of what it actually is. So say you have a nucleus right here, and this nucleus is normally proton rich, so it doesn't have enough neutrons, but it has a lot of protons for the given number of neutrons. Now, what it's going to do is it wants to convert all these excess protons into neutrons. So how's it going to do that? Well, thankfully, there are lots of orbiting electrons, and we know that when we combine protons and electrons, we get neutrons. So here's a proton in the nucleus, and here's the electron. This nucleus will literally capture the electron from the shell that it's orbiting in and create a neutron. And this will normally spit out an electron neutrino. So let's draw a little diagram. So at the bottom we have our proton that's going in. Protons are the reactants in this case. And you have the electron that's orbiting. So remember, leptons are always on the left. Now, because the electron is actually incoming rather than going out, it's the W plus boson. So you know I said that rule before, when you have the outgoing sign of the electron always matches the sign of the W boson. Well, it's actually reversed if the electron is incoming. So you've got the W plus boson that's responsible for electron capture. And what are the products? Well, we've got the neutron right here, and we also have the electron neutrino, and it's a normal electron neutrino. So in summary, we have the photon, which is the force carrier of the electromagnetic interaction. We have the W plus or minus boson, which is the force carrier for the weak interaction. Now, as for the strong nuclear force, that also has its own particle, which is called the gluon, and that's normally given the symbol G. And that's the particle, that's the exchange particle that's responsible for binding the nucleus together. You know, we said how the strong nuclear force was the one that bound the nucleus together. Well, the particle, the exchange particle, which is responsible for that, is the gluon. But what about gravity? Scientists think there is actually a carrier force due to gravity, which is called the graviton, but it has never been detected in any detector at all. So at this point, it's still theoretical. So I hope that helps, and I'll see you in the next video.